Okay, let me just do a mic check. Seems like we are live. Welcome to another tech day live from my bedroom slash workstation. What I have planned for today is to continue with the chapter on training linear models for machine learning, and afterwards, because my dream is to build a game, I celebrated a birthday recently, and I realized, man, I don't have enough time to do what I want, and I really want to build a game. So hopefully, if I finish this in 1 hour, I can do the second one on Unity and on building my knowledge in order to succeed in building my game. So let me just see what we have here. We have something called regularized linear models, which I have no idea what the title means. So hopefully what I can do here is, again, I'm following a book. It's a great book called Hands-on Machine Learning with Scikit Keras and TensorFlow. But some of the things are not as clear as they should be, because, well, these are the perils of following a technical handbook. So a lot of my things I need to ask ChatGPT, and I need to specifically tell him to explain me these concepts like I'm a 5-year-old. So okay. Wait, let me move my window here. Yeah. For some reason, he remembered that I told him from the last stream that I told him, please talk to me like I'm a really smart 5-year-old, and now he's cuddling me. But okay, what's a linear model? Imagine you're building a block tower. Each block is a number. Each block is a number. Like height, weight, age, and the tower is your prediction. A linear model says, let's stack the blocks in the best way so they add up to the right number. Like this, block 1 plus block 2 plus block 3. Now imagine you have too many blocks and some are weird, heavy, or shaky. Okay, your tower still works, but it leans too much. It might fall over on new floors, and that's called overfitting. Yeah. So the concept of regularized linear models is closely related to the concept of overfitting, which means that regularization is saying, okay, don't go crazy with the blocks, keep them small and neat. Small and neat. All right. So we have 3 types of regularizations. We have ridge, regression, lasso, and elasticnet. Okay, so what does the book says? A good way to reduce overfitting. Okay, now, what's overfitting? What is overfitting? A good way to reduce overfitting is to regularize the model, which means to constrain it. The fewer degrees of freedom it has, the harder it will be for it to overfit the data. A simple way to regularize a model is to reduce the number of polynomial degrees. But first of all, what's overfitting? Where's my tablet? It should be here somewhere. Yeah. we have regularized linear models. I haven't said that word correctly once during this whole stream. But okay, so there's a concept called overfitting that I'm gonna explain it right now. So overfitting. Again, ChatGPT is giving great examples here. Imagine you're learning to cook spaghetti. Okay. And you make it for your friend, and your friend, hopefully I didn't draw anyone famous, and your friend says, okay, I love when the spaghetti is super salty and the noodles are extra soft. So the next time we cook spaghetti for our friend Alex, we cook them just like they want. It's super salty, it's soft. And you measure the salt like into the milligram, you measure the salt. But now we are serving the same noodles to another one of our friends. Let's call him Jordan. And he hates the noodles because Jordan doesn't like salt at all. And that's basically overfitting. We are trying to perfectly match one person's taste that we forgot to cook spaghetti for everyone else. In machine learning terms, it means that, okay, our model is learning from the training data. If it memorizes the training data too perfectly, it won't do good on new unseen data. And that's overfitting. Model learns from training data. Okay, model learns from training data. If it does too well on training data, it won't do good on new data, and that's basically overfitting in a nutshell. So we will have low training errors, which means it's great performance on the data we already know, but we will have high validation errors, which means it's gonna perform poorly on new data. So yeah, overfitting happens when our model is too complex and starts capturing random noise or, you know, some specific quirk of the training set instead of real patterns. And that's basically the point of it. If our model is trying too hard to be perfect, we can calm it down by putting rules or limits on it. And now that's how we solve overfitting, by regularization. Yeah, I said it. I said it correctly this time. So for example, if we have a model which looks like this, so this is the base, bx times cx squared times dx cubed times ex to the fourth. We can regularize or simplify this by removing the high powers. We can simplify it by leaving only this a bx plus cx squared, which makes the model simpler, less flexible, and less likely less likely to overfit. Okay, now I'm gonna hit ridge regression, and I for some reason this will have a lot mathematics. So if you are bad at it like I am, let's get ready for some real head scratchers here. Okay. Okay, so let's look at the code here. Okay, so this generates a random seed. We have 20. Oh, I need to run everything above. There is no NumPy library here. Okay. Man, I bought, initially I had 2 sticks of 8 gigabytes of RAM, and the notebooks were running relatively slowly, I would say. And now I got 2 new sticks of 32 gigabytes each. And for some reason, it still doesn't. It's not instant. I want it to be instant. How did our forefathers worked on those old clunky machines? Okay, is it working? It is working. Okay, 20, what's this? 20 items. We have an X, we have a Y. Wait, what's being done here? Let me check. Print X, print Y. These are most probably, yeah, vectors, and they were generated randomly. What else do I have here? Wait, where's my tablet? Okay, just a second. Okay, random seed. I won't even comment on this one. We make sure that the random numbers are the same every time we run the code. That's what MP random seed does. Now, 20 makes 20 data points. Now, the X will generate 20. First of all, this will generate 20 random numbers between 0 and 1. And it's gonna multiply them by 3, which means that it's gonna scale all numbers to be between 0 and 3. So we are creating 20 input values. We're gonna have a vector that will contain values such as 1.2, I don't know, wait, 1.2, 2.7, 0.5, and so on. And we are gonna generate 20 of these in this vector. Ah, here they are. So we have 20 of these. 1, 1, 2, 8, 2, 1, 9, blah, 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 2, 9. So from 0 to 3. Okay. Now, y is our target value. What kind of data will it create? What kind of formula is this? So it's y is equal to 1 plus 1/2, because it's 1/2 x plus It's creating a random number between 0 and 1 and it's dividing it by 1, 5. Okay, this is usually used to create noise. I don't want to make the target value too perfect because we need to train on it. So this will create some noise, but why is it dividing it by 1.5? Why is it dividing it by 1.5? Oh, there are 3 people watching this. Thank you, thank you, thank you. I don't know why you do this. I'm not an expert in this. But if you want to watch me struggle understanding why is this divided by 1.5, please do. Okay, so ChatGPT says, okay, this will create some noise like we did in some snippets above, but this will regulate the noise a bit better. It's gonna reduce the noise so it's not overwhelming. And why we haven't done this before? Okay, this will create from 0 to 300 numbers. Reshape what is turning them into columns. So if I run this again and if I run this below, okay, I plotted X and Y here. I plotted X and Y here. Hi. Yeah, I'm funny. I plotted X and Y here. Okay, so we import ridge. Oh man, what the fuck? What the fuck? What will we do with the linspace that we created with these values here? Will we ever reuse them? Wait. Let me get some theory on what this is before I even continue looking at this. Okay, until now I know this first snippet. There is a pretend dataset. Like, I don't know. We draw a line with a shaky hand or some bullshit. And we want to train the model that will know, okay, the model will understand what the pattern between this is, hopefully. But what is ridge regression? Okay. Okay. What is ridge regression? Let's say I have these same dots here. Bam, 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 bam. Wait. Here they are. Bam, 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 bam. Okay. And I want to draw a line, okay, that will fit all of these dots. Linearly, what does it mean to solve this via linear regression? Is to just draw a line like this. and the line should be approximately at a decent distance between all of these points. That's linear regression. But what if we have all of these same points, but instead of this line, let me put another color, instead of this line, I do something like this. This basically means that the line is bending and stretching to touch every dot exactly, which ties into the concept of overfitting that I explained back then. So what we are doing, we are using this ridge regression to say, okay, don't do this too far, don't overfit it, keep this tidy and small. And the difference is, so the regular linear regression. The regular linear regression is trying to minimize the error between prediction and actual values. And it uses MSI, mean squared error, as a cost function to minimize this line. Basically, what MSI is nothing more than the distance between the line that we are solving, that we created to solve all of these points, and the points of it. So the smaller the distance, again, we can fit every one of these points, but we should reduce the distance, and the line should be, okay, I messed up. And the line should be straight. So we won't fit all the points, but we should fit them optimally. But what the ridge regression does is it tries to minimize the error and keeps the weights small. Oh, you must be fucking kidding me. What does this mean? What does this mean? Where's the formula for this? So we are adding a regularization term equal to something to the MSI. And this will force the learning algorithm to not only fit the data, but also keep the model weights as small as possible. Okay, so for ridge regression, we are using the same thing. We are using the mean squared error. Okay. Hey, thanks for joining the live. I'm trying to learn and grasp machine learning as a concept. And currently, so basically, I'm trying to I'm a web developer, I'm a software engineer, and I'm trying to switch my career, and we are all gonna be booted by AI sooner or later. So I thought, okay, let me maybe join the enemy, and that's what I'm learning. And this is basically not only using LLMs and all of these AI models that are freely available and have an interface open to users. This is like all of this heavy math. Basically, right now at this point, we are trying to train linear models to solve examples, and I'm gonna do one of these for ridge regression right now. So if you stay, maybe you can maybe you can find something interesting. Maybe I can find something interesting as well. Hopefully. So this is the cost function. This is the cost function. So, and I multiply it by alpha. So I don't multiply it. This is my mean squared error plus alpha. Yeah, I am. It's self-study. I finished university a couple of years back to be a computer scientist. So I'm not studying from teachers. I have this book that a lot of universities use, and I'm just going step by step. I'm trying to cover the whole book for machine learning. Again, this is something that I'm planning to do just to get bread on the table. My real dream is to build a game. And also I installed Unity as well, so maybe I'll do some Unity later on. Sum of squares of weights. So this is the regularization term. And that's the only thing I assume what defines ridge regression, that you have this regularization term. Hey, welcome. I'm a student from business background. Okay. What do I have here? So we try to minimize the error and keep the weight small. And we have this regularization term. And we have a ridge regression cost function, which looks like this. J of theta is MSI of theta plus alpha over M. What the fuck? And the sum of I of all the thetas of square. Wait, can I do an example of this? And I learned C and Python. Man, C and Python are the best languages to learn. For some reason, the idiots at my university gave us only while I was studying. So in the first year, we only had like one semester of C, and then they said, you know what's really popping off? Web. So let's from the second semester of the first year, let's mostly do JavaScript, and we did Python and C, but for niche classes like data mining and stuff like this. All the big, I would say big classes, but okay, introduction to programming was C, advanced programming was also C, actually C++, and then project building was JavaScript. We have web development, which was JavaScript, software engineering, which was okay, it was Python, but we also had to use a front end, so it was also JavaScript. Like learning Python and C is really good. I think. Okay. Okay, let's do a tiny data example of this, because I also don't understand how this works. Okay, let me just move to a new page. let's say I create a new x, and x is an numpy array. So it's not a regular array, it's a numpy array. 1 1 1 2 1 3 1. No, let's change this a bit. So let's make this 2 2 2 3 3 5. And I have the target values, which will be again a numpy array, but it's gonna have, let's say, 5 7 9 11 and 15. Okay, so why do I have two values here? Because these are two input features per row. I don't know, let's say how many, one of them is how many times we spent working on something, and this is how many cups of coffee we had to produce, how many points we have on an exam. I don't know, let's say this is it. So then I can pull up a linear regression model, and I can fit it on x and y. Okay, wait, let me do this above here. Code. Okay. So I have this. And y is also an numpy array 5 7